Hello and welcome to this session in which we will look at another data type called queue, which also has its values as sequences, but it differs from say a stack in terms of the operations that can be performed on it. So what is a queue? So as I said, it's another data type whose value is a sequence only, but the operations that you can perform are different. So queues you are familiar with from ordinary usage. They are used whenever resources have to be shared. So when you want to enter a bus, you have to form a queue because many people want to use the bus. Similarly, when you want to print a file, the printer uses a queue to store all the files that need to be printed. So this is also what is called a first in first out structure or a FIFO structure, where an element which enters the queue first will come out of the queue earlier, whereas a stack is a last in first out structure. The element that entered the stack last will be the first one to come out of the stack. So in a queue, elements are popped in the order they are pushed in the queue. So let's define queues formally. So what are the allowed operations? They are very similar to those for a stack except for the insert operation. So there is the empty operation again, which tests whether a queue is true, whether a queue is empty or not. So it is true only for phi, and for a queue obtained by pushing an element in any list, it is also false. The insert operation is defined differently in the case of a queue compared to the push operation in a stack. If you insert in an empty queue, you get a queue which contains just that element, which is obtained by pushing that element x in an empty sequence. If you insert an element x in a queue which already has an element y pushed into some sequence s, then you insert x in the sequence s and then push y into that result. So here essentially x gets inserted at the end of the queue when you are inserting in a queue, whereas in a stack a push would have got inserted at the beginning of the stack itself. Pop operation is similar for a stack as well as a queue. Pop for an empty queue is undefined, which means it will give an error if you try to execute it, and pop of a queue whose value is push x comma s is the queue obtained by removing the element x. The front is again similar to the top operation of a stack. Front is undefined if the queue is empty, and front of push x comma s is the element x, which is at the beginning of the sequence. So here only the insert operation is different from the stack, but queues have different properties because of this. So let's look at a property of a queue. So this says that if the queue is not empty, then the front of the queue obtained by inserting an element x in the queue is equal to the original front of the queue. That is, the element at the front of the queue does not change if you insert an element in a non-empty queue. Note that if the queue was empty, then front of queue was not defined earlier, whereas after you insert an element x in it, it will be defined. So this equation will not be valid if queue was empty, because front queue is not defined in that case. So inserting in a non-empty queue does not change its front element. So we will try to prove this formally. This is not true for a stack, for example. If you push an element in a stack, the top of the stack changes. So this is different from that for a stack, whereas in a queue the front remains unchanged even after an insertion. So we will prove when the base case now we consider is not the empty queue, but the queue having one element whose value is obtained by pushing an element y into the empty sequence. Okay, so let us prove formally that the front of a queue remains unchanged if you insert an element in a non-empty queue. So essentially we first consider a queue with single element, which is push y comma phi. If I insert x into such a queue, by definition its value is obtained by pushing y in the queue obtained by inserting x in phi, and by definition of the front operation this value is equal to y in both the cases. So front of push y comma insert x comma phi is defined to be y by the definition of front, and front of push y comma phi is also defined to be y. So both sides become y and the equality holds for this. Now consider a queue with two or more elements. we can write such a queue as push y comma push z comma s, where s is any sequence with 0 or more elements. And now we insert x into such a queue. By definition, the resulting queue can be written as obtained by pushing y in the queue obtained by inserting x in push z comma x. The front of this is always y by definition, and this is also equal to the front of the queue obtained by pushing y in push z comma s. So again, this equality holds for queues of size greater than or equal to 2. Assume in this case actually we do not really need the induction hypothesis, but directly we can show that the front remains the same for both queues, but you need to do it for the base case as well as for queues of larger length. So let us define some functions of queues, and we can use queue operations themselves to define these functions. So one way is to look at possible values of a queue. The standard way we have been using to define operations is to define for the empty queue, and assuming it is defined for a queue x or queue s, you define it for the queue push x comma s. But instead we can also define it using the already defined operations on a queue. So now look at a function like size of queue. So if queue is empty, or if empty queue is true, then the size is 0, else we remove one element from the queue. So look at size of pop queue and return the next element of that as the size of the queue. So this just says that pop queue reduces the size of the queue by 1. So here is another operation called shift, which takes the element at the front of the queue and puts it at the back. So if empty queue, then it does not do anything to the queue remains as it is, it is empty. Else we call insert front of queue into pop queue. So this operation takes the front element, removes it from the queue, that gives you the queue pop queue, and now it inserts the front element into the result of popping the front element from the queue, which will put this element at the end of the queue. So this you can think of it as a circular shift operation on the queue, but note that it is easy to define using the already defined operations on the queue. So here is another way of reversing a queue using only these operations. Again, if the queue is empty, it is nothing, else all that we need to do is remove the front element of the queue, reverse the remaining queue which is pop queue, and now insert the front element in that queue. And note that insert operation puts it at the end of the queue. So this will essentially give you the reverse of the original queue. Okay. So these operations are well defined because pop queue has smaller size than queue, and therefore we are using induction here. To be formally precise, we should have done it in the earlier way, define it when the queue is empty and define it for when the value of the queue is obtained by pushing an element into the queue, into some smaller queue. In this case, we are assuming it is defined for the queue pop queue, and then you are defining it for queue. So here are some exercises that you can try to do. So again, try to prove that reverse of q is equal to q for any q. Now consider this function f q comma I that takes a q q and a number I as a parameter, and it is defined as follows. F q comma 0 is q for all q's q. So if I is 0, then it does not do anything to the q. F of q comma next I is shift f of q comma I. Right? And so prove that, so what this, we have defined the shift operation as removing the first element of the queue and putting it at the end of the queue, right. So if we apply this operation size q times, we should get back the same q as the original q. So try to prove the formulae that f of q comma size q is always equal to q for all q's q, right. And now what q's will satisfy the property that if you shift this once, you will get back the same q, that f of q comma next 0 is essentially 1. So if you apply this operation once, when will you get back the same q? Not all q's will satisfy this property, but you can find out exactly which q's have these properties. So try these exercises and we will meet next time. Thank you.